Welcome to class, students. Happy Wednesday, hump day. All right, so we have 2 days of notes so far. Take a moment, read the question for bell work, pause as necessary, have the sub go around, stamp your papers for worksheet number 2 if it's complete. And for you slackers, make sure that you go home and complete that so that you don't get more than just -10 for not having it complete today. If you were absent, write absent at the top of your paper, okay? But you still need to complete the homework. Let's read the bell work question, and then you can have the sub pause the video so that you can complete it. 150 milliliters of 2.55 molar sulfuric acid reacts with 1.89 molar potassium hydroxide in a neutralization reaction, which means acids and bases. What volume in liters of potassium hydroxide is consumed? So let's start off by writing our equation. Sulfuric acid is H2SO4. We are mixing it with potassium hydroxide, KOH. So we are mixing a strong acid, strong base, ionizing completely into H plus and OH minus. We form water as a product of neutralization. Let's look at what happens to SO4. SO4 has a -2 charge from 2 ionizations of hydrogen. Potassium has a +1 alkali earth metal. When we crisscross, we want to write potassium first, so we are going to get K2SO4, potassium sulfate. And I'm going to erase all of this. So let's set up our dimensional analysis after we write down what we know. We know that we have 150 milliliters. Oh, that's messy. Well, we have 150 milliliters of a 2.55 molar solution, and it reacts with a 1.89 molar solution of KOH. So we know the concentration of KOH. We're not trying to find that. We are trying to find what volume we have, okay, what volume we need to neutralize it, to put it to its equivalence point. So this is what we are looking for. And specifically, probably end up in liters because the units of molarity are in liters. Here's my dimensional analysis problem. I'm starting out with 150 mils. I'm going to put that into liters. Okay, 1,000 milliliters in 1 liter. I'm going to use molarity. There are 2.55 moles per liter. That is my concentration. Did I look and see if my equation was balanced? Okay. No, I don't think I did. So I'm going to go back and do that to make sure that everything is balanced out. Okay. So what I'm seeing here is that potassiums are not balanced. So I'm going to put a 2 in front of this K to balance out the 2 potassiums. And that's going to give me 2 oxygens. So I'm going to put a 2 here. And I believe everything now is balanced. So make sure that's balanced. You have to balance your equation because otherwise you may not get the right stoichiometric mole-to-mole ratio. So everything up to this point has been H2SO4, H2SO4, and then this was H2SO4. So now what's going to happen is I'm going to use my 1 mole of H2SO4 to 2 moles of KOH to go from one to the other. That is my stoichiometric mole-to-mole ratio here. And now what I can do is use the molarity given, which is 1.89 moles per liter of KOH. And what I get is liters of KOH. And that answer is And I got an answer of 0.405 liters. Today we're going to look at buffers. We have like 8 slides. After today, you will begin working on worksheet number 3 of the packet. Yep, this is what you get when Dawkins gone. But make sure that you're continuing staying updated with the homework packet. So let's look at buffers. Solutions which resist change in pH when small amounts of acid or bases are added. Buffers are huge in fish tanks. Buffers are huge in pH meters, keeping them clean. Those little white bottles that we did in the acid-base lab that went on the pH meters, those are buffers, and they resist large changes in pH. Our bodies are huge buffers, and we're going to learn about that on the last slide here. Buffers consist of weak acids and weak bases because they ionize and they can kind of help buffer. Buffer capacity is the amount of acid or base that a buffer can absorb without large changes in pH. So basically the buffer capacity is like the max amount that it can absorb without actually starting to have major changes in pH. And I mean, what are the uses of this? Well, I mean, if we can resist changes in pH, we can maintain certain systems. And certain reactions will only occur at certain pHs. So this is very important. Buffers are super important. So fill these in your notes. This one is, let's look at acetic acid / acetate systems. So in the last test with pH and OH, we looked at ionization, and we looked at conjugate acids, conjugate bases. And so now we are going to look at buffers associated with these. We know, okay, let's look at the first part here. We know that we can add a hydrogen to acetate, which will give us HC2H3O2, or acetic acid. Okay. So if we have, and let's see if I can draw this well. If we have acetate floating around in solution, and we have a bunch of H pluses that are being introduced, which means that we are lowering the pH, or we are trying to, what happens is this acetate comes in, and it will start absorbing these H pluses and turning them into a neutral acetic acid compound. And so what's good about that is there is no charge associated with this, no H plus ions left floating around, and so the pH cannot drop. If we flip it around, look at the other side. If we have OH floating around everywhere, okay, if we have OHs, let's go back here. If we have OHs floating around, and I cannot draw today, we have lots of OHs floating around. What's going to happen there is the pH is going to try to increase. But if we have this acetic acid here, it is going to start eating up all of these OH hydroxides. And we're going to be resulting in acetate ions, okay, being formed. But what happens is the hydroxides form water. And when they form water, they're no longer hydroxide ions floating around, increasing the pH. And so again, this is a mechanism, this is a way, these buffers are ways of stopping the pH from rising and falling. Another buffer example here would be the addition of H+. And so let me just stop and talk real quick about these and why we need to know these. Number one, because they keep systems at a certain pH, and that's a great thing. Number two, we need to be able to look at a certain set or a pair of ions and their weak acids and weak bases, and we need to look and be able to identify which one would be a buffer for H plus and which one would be a buffer for OH. So I would ask you, okay, if we want to stop the pH from rising, what would we do? Or if I wanted to stop the pH from lowering, what would we do, or what would we add? Okay. So go ahead and write these in. I think NH4 is already plugged in for you, but the same thing as the previous slide, we're going to have OH floating, or sorry, H plus floating around in solution. NH3 is going to come in, swoop up, and start collecting these H pluses so that we do not have a decrease in pH. When the OHs are floating around, we're going to have ammonium come in and eat up all of those hydroxides so that we do not form a pH that starts to increase. Another one that we need to know is going to be the carbonic acid hydrogen carbonate system. And this one's huge for bodily functions. And we'll look at this in a second. Same thing though, I won't spend a whole lot of time on it. Pause it if you need to, go back if you have questions. I'm going to let you take a second to fill this in. But the carbonate ion here is going to, or the hydrogen carbonate ion is going to eat up any H plus introduced, which will prevent the pH from lowering. Okay, and here, man, I cannot figure this tool out today. And here, the OH, this carbonic acid will come in and eat it up and will prevent pH from rising. So take a second, and I want you to show how the addition of an acid would affect the H2PO4 minus and HPO4 2 minus buffer system. So again, real quick before I have the substitute pause the video, we are adding an acid. And what do acids contribute? Our Bronsted-Lowry definition says that acids donate hydrogen. So we are donating hydrogen. How is that going to affect this buffer system? So pause the video, and I'm going to come back in a second. Alright, so if we are introducing H plus into our solution, remember that this could also be H3O plus. We need to figure out which one of these is going to need to be present so that we can eat up all of these hydrogens. Okay. So we have two choices. We have H2PO4 minus, and we have HPO4 minus 2. Well, the one that we want is going to be HPO4 2 minus because it has a greater capacity of picking up these hydrogen ions. Okay. So the way we would show that is we would show that HPO4 minus 2 is going to pick up these H pluses and form H2PO4 minus 2. So this is what I wanted out of this question. Let's look at buffers in the blood. When a strong acid or base reacts with a buffer, one part of the buffer changes into the other, right? We have this back and forth with this buffer. Buffers are important because we have to have blood at a certain pH. Otherwise, we start getting very sick. Body systems will shut down. Cells will begin to lyse and break up and die. Blood must maintain a pH of 7.3 to 7.4. 7.4 they call the ideal pH for human bodies. The buffer systems in the blood, this is the big one, and this is for when we have an increase or decrease in carbon dioxide. So if we're getting enough air, the capillaries in our blood, in our bodies that carry blood, they are introduced to CO2. And CO2 reacts with water just like I showed you in the dry ice demo, and it forms carbonic acid, which eventually will cause carbonate ions to form. And so that's where it comes from, just like I showed in the dry ice demonstration with the indicators. And what happens is these carbonic acid and hydrogen carbonate ions will buffer back and forth to keep the pH of the blood at a certain level. They want to keep it at this 7.4. And another one to note in the body would be the H2PO4 dihydrogen phosphate and hydrogen phosphate buffer system as well. Okay, Okay, so we need to know these two, that they are in the body. These are body buffer systems. So quick question, and then we are finished with notes. I'm going to let you go free and work on your worksheet number 3. Why are buffers important in the body? Okay, so pause it for a second, otherwise I'm going to go ahead and continue. Buffers are important to the body because they maintain, and this is just true for buffers in general, but they maintain a certain pH. You could take it a step further and say that cells that you learned about in biology need a pH to carry out certain functions. Certain functions like muscle twitching so that you can lift objects. What else? Cells will transport materials so that you have the right nutrients. If you don't have this pH, the cells can't do their jobs, and we begin to break down. We begin to die. So with that fun note, we are finished with notes. Use the rest of class to work on worksheet 3, and I will see you tomorrow.